Hey guys, today I'm going to be talking about equipotential and field lines. So in order to understand this, you're going to have a really good grasp on the concept of field lines before we can get into equipotentials. So as you can see, I've already drawn out some field lines, and they always originate right in the center with something called a point charge right here. And that point charge, although technically isn't charged, we kind of treat it like a proton. So a positively charged particle right there in the middle. And so all of these field lines, you can see the arrows are all going outwards. And so it represents the direction that a proton would travel in this field, if that makes any sense. So in order to understand that, we can get into what equipotential lines are. And as you can see, it kind of says it in the word itself, equipotential, meaning equal potential or same potential. And so what I'm going to do is I'm going to draw some equipotential lines for you guys and then explain them. So here you go, there's 3 for you right there. Okay, so what equipotential lines mean is that any point on the equipotential line has the same potential. And so on each of these lines, as you can see, if we had a point here versus a point, let's say right here, both of these points would have the same voltage. And if you look at the relationship between equipotential lines and the field lines, you can see that each of these are perpendicular to the field lines. And that's super important to remember. There's two kind of really important things just conceptually that you have to remember. The first is that they are perpendicular to field lines. I can't really read that. Perpendicular to field lines. And the second thing to remember is they can never cross. Okay, so like this line right here can never cross with this line right there. And so that's kind of the definition of equipotential lines and how to visualize them. And so, I mentioned earlier that each point on one equipotential line has the same voltage. And so if we kind of put that into an equation for you guys to understand how this all works, we can relate it to the work equation. So I'm going to write that right over here. And there's two different work equations that we know, and so I'm going to go through both of them and kind of how this relates to solving for work and understanding what work is required. So work is defined as the change in negative potential energy, or a different way to write that is negative Q delta V. So the Q right there, the charge, is going to have a numerical value, but the change of V, if they're on the same equipotential line, means they have the exact same voltage, which means that V is going to be 0. And so we can conclude that work is also 0 in that case. So to move from this point to this point requires no work. Another way to kind of visualize that is by thinking of a different equation that we've learned in the past, that work is also equal to force times distance times cosine theta. And in this case, that angle that they're talking about is the angle between the electric field line and the equipotential line. And so as I've already drawn here, you can see that they are perpendicular to each other. And so this would be cosine of 90 degrees, which is 0. And so work is 0. That's just another way to kind of visualize it or to think about it with those two equations. And so as you can see just in this figure specifically, the field lines are all really straight, and there's only one charge in the middle. And so the equipotential lines are very concentric and symmetrical, but that's not always the case. If you look here, when there are two charges acting on a field, you've got all of these crazy electric field lines that are going out like this, and they're not all in straight lines. But as you can see, these equipotential lines in green are still perpendicular to each of those field lines. So that's really important to remember. Equipotential lines aren't equal in shape as in a perfect circle, but they have the same voltage around that equipotential line. And so they always have to be perpendicular to the field lines. And just over here on the right, between two metal plates, you can just see another visualization of this. And so the equipotential line in this case is this 75 voltage and 25 voltage lines that are traveling down like this. So these are your equipotential lines, and the ones going from positive to negative are your field lines. And I said this before, but that's really important to understand, that your field goes in the direction that a proton would travel in that field. And so it always will go from positive towards the negative side. I'm now going to go over just a few different problems, some stuff that you might see in quizzes or tests in the future that kind of envelop this concept. And so hopefully I can go through it and you guys will have a better idea of what this means and how to apply it into the problems that you'll be working with. So as I've drawn a kind of a similar diagram as the one before, where electric field lines are going out in all directions and there's a positive point charge in the middle, and then there are different points located at different equipotential lines, and then their values are given kind of on the bottom right. So we're just going to go through these one by one. The first one, how much work is required for a 20 microcoulomb charge to move from point A to point B? Well, if we look back at our diagram, point A and point B are on the exact same equipotential line. And so we know that the change of voltage will be 0. But just to show you the equation that we need to use, work equals that negative charge times the change in voltage. And so because we go from 400 to 400, the change in voltage is 0, which just means that our work is 0. So there's no work required to move that point charge anywhere along that line because it has the same voltage. So pretty straightforward. If we move on to the second equation, how much work is required to move a positive 32 microcoulomb charge from point C to point D? So if we look at our diagram, point C is on a different equipotential line than point D. So to move it will require work. So I'll go through that equation with you. So as we know, work equals the negative charge times delta V. And you want to make sure that your charge is always in coulombs. And so in this case, 32 microcoulombs is 32 times 10 to the negative 6 coulombs. So make sure you remember to do that. So our work would be equal to a negative 32 times 10 to the negative 6 coulombs. And then our change in voltage, you always do final minus initial. And so D minus C. So in this case, it would be 100 volts minus 300 volts. And then if you plug that into your calculator, you will get work equals 6.4 times 10 to the negative 3 joules. Well, how did I get joules? So, your charge, Q, that's right here, is in coulombs for your units. And your voltage is in joules per coulomb. So if we multiply those, the C's will cancel out and you're left with joules. Okay, so that's kind of how you end up with your unit for work. And then we'll solve the third one. So this is how much work is required to move that point from C to D. Now, if we go on to 3, and hopefully I'll have enough room for this, but how much work is required to move a proton from point A to point D? So, same equation, work equals negative Q delta V, and in this case, they tell us we're working with a proton. Well, they don't give it to us, but it is a given. So the charge of a proton is equal to 1.6 times 10 to the negative 19 coulombs. So now we can plug that in. So work equals negative 1.6 times 10 to the negative 19 coulombs times, and then we're moving from point A to D, so it'll be final minus initial. D is 100 minus A is 400. So work in this case is equal to 4.8 times 10 to the negative 17 joules. And the reason there's such a drastic difference or change in work for both of these is because you have to take the charge into account. This charge right here in problem 2 is 10 to the negative 6, whereas this charge in problem 3 is 10 to the negative 19. So it's a much smaller charge, so a lot less work is necessary to move that charge. And it also depends on how far you're moving it or across which equipotential lines you're moving it. That will determine how much work is required. So another common question that you'll see is, what is the magnitude of the electric field shown? And so if you look here, what you're given are the two equipotential lines. So I'm just going to abbreviate this equipotential lines right here because across this whole line, it's 70 volts. Okay, so just kind of visualization. But they're asking about the electric field. And so what you need to do is understand which direction your electric field is going and then find the magnitude of it. So electric field lines always go from positive to negative, but also from high to low potential. And so this bottom one right here is actually your higher potential. So it'll go from high to low. So all of your lines look like this. Okay, and then your equation to find the magnitude of the electric field is E equals negative change in volts over the distance. And we're given distance right here is 2 meters. So E is negative, final minus initial, right? 70 volts minus 500 volts over 2 meters. And then if we solve that numerator, we get a positive 430 volts over 2 meters, and that leaves us with a magnitude electric field of 215 volts. So that's how you solve for the magnitude. And these are just some basic equations that I've gone over, and very, very common questions you'll be asked regarding this concept.